Students, in design of transmission system, the unit name is sliding and rolling contact bearing. Today we discuss about Reynolds equation. In Reynolds equation, this is the Reynolds equation. The analysis of hydrodynamic lubrication is summarized a different equation derived by Reynold. Each different equation is used as a fundamental equation for hydrodynamic lubrication and properly known as Reynolds equation. The assumptions. The theory of hydrodynamic lubrication is based on a different equation derived by Reynold. This equation based on the following assumptions. The lubricant obeys Newton's law of viscosity. The lubricant is incompressible. The inertia force in the oil film are negligible. The viscosity of the lubricant is constant. The effect of curvature of the film with respect to film thickness is neglected. It is assumed that the film is so thin that the pressure is contact across the film thickness. The shaft and the bearing are rigid. There is continuous supply of lubricant. An element having dimensions dx, dy and dz is considered in this analysis and is shown in figure. X is the axis in the direction of motion, y is the axis in the radial plane and z is the axis parallel to the axis of the journal. U, v and w are velocities in x, y, z directions respectively. Tau x and tau z are shear stresses along x and z direction, while P is the fluid film pressure. So this is the diagram. This is the bearing, this is the fluid element, this is WO1 shaft, this is the H thickness. So this is the bearing, this is the oil groove, this is the fluid element, this is shaft, the distance D, this is fluid element in YZ plane. So the following forces acting on the element X direction as shown in figure. Consider the equilibrium forces Dabba tau x by dabba y into dy dx dz is equal to dabba p by dabba x into dx dy dz. So in this diagram, the distance dx dy tau x, so the forces is p dabba rho by dabba x into dx and tau x plus dabba tau x plus dabba y into dy. So the equation is dabba dabba by x h cube dabba p upon dabba x plus dabba by dabba z h cube dabba p by dabba z 6 mu u dabba h by dabba x. The above equation is known as Reynolds equation. There is no exact analytical solution for this equation for bearing with finite length. Theoretically, exact solution can be obtained if the bearings is assumed to be either infinitely long or very short. These two solutions are called Sommerfield's solution. Approximate solution using numerical methods are available for bearings with finite length. So, in Reynold and Boyd method, there is no exact solution to Reynolds solution for a journal bearing having a finite length. However, Reynold and John Boyd of Westinghouse Research Laboratory solved this equation on computer. Using the iteration technique, the results of this work are available in the form of charts and tables. In the Reynold and Boyd method, the performance of the bearing is expressed in terms of dimensionless parameters. Table gives values of these parameters for a full journal bearing with side flow. So, in figure, O and O dash are the axes of bearing and journal respectively. The distance O dash is called eccentricity and denoted by the letter E. The radial clearance C is given by C is equal to capital R minus R. This is the shaft, this is the bearing, this is the HO, this is the NS, EO and this is distance R. Where C is equal to radial clearance in mm, capital R is equal to radius of bearing mm, small r is equal to radius of journal mm. The eccentricity ratio epsilon is defined as the ratio of eccentricity to radial clearance. Therefore, epsilon is equal to E upon C, where epsilon is the eccentricity ratio. R is equal to E plus R plus H0, where H0 is equal to minimum film thickness. Substituting this equation in expression, C is equal to R minus R is equal to E plus H0, that is equal to C into epsilon plus H0, or C into 1 minus epsilon is equal to H0. Epsilon is equal to minus 1 minus H0 upon C. The quantity H0 upon C is called the minimum film thickness available. The Sommerfeld number is given by S is equal to R upon C bracket square mu ns upon P, where S is equal to Sommerfeld number bracket dimensionless, mu is equal to viscosity of the lubricant, ns is equal to journal speed, small p is equal to unit bearing pressure, that is load per unit of the projected area. The Sommerfeld number contains all variables which are controlled by the designer. So, the angle phi shown in figure is called the angle of eccentricity or attitude angle. It locates the position of minimum film thickness with respect to the direction of load. The value of phi given in table are shown in degrees. The coefficient of friction variable CFV is given by, this is the table. So CFV is equal to R by C into F, where F is the coefficient of friction. The frictional torque is given by MTF is equal to FWR Newton per mm. Frictional power 2 pi ns FWR Newton per mm per second. Therefore, KWF is equal to 2 pi ns FWR upon 10 raised to 6, where L is equal to length of the bearing in mm, Q is equal to flow of the lubricant mm cube per second. In this case, Q represents the total flow of the lubricating oil, a part of which is circulated around the periphery of the journal, while the remaining oil flows out as side leakage. QS represents the side leakage, which can be calculated from the value of parameter QS upon Q given in the table. This is the table. So, thanks all of you.